Hi everyone, my name is Miss Hu and I am a physics teacher. In this video, I am going to show you how to solve problems involving forces of equilibrium where the angles are not equal to each other. If you would like to know how to solve the problems where the forces are acting at angles equal to each other, do check out my earlier video which I have addressed this. Also, it would be good for you to watch that video first as a foundation because understanding how to solve the problems in that situation will definitely help you understand how to solve this situation more easily. So to solve this kind of question, just like for forces that are acting at an equal angle to each other, you can also solve this question using calculation or the scale diagram method. So in this video, I will show you both methods as well. So before we get started, let's talk about the triangle of forces first. Remember that the arrows in the triangle must form a continuous loop. So you can either draw a triangle this way. So starting with the weight line, because the weight line is on this side, you can have your tension to draw first. So this would be T2 and this would be T1. That means the angle of 25 is here. So this would be 65. And here, this would be 50 degrees. That means inside is 40 degrees. And here, this would be 25. Or you could draw it the other way. That means the weight line here is followed by T1, then T2. So whether you use this triangle or this triangle is perfectly fine because both are correct triangles for this question. Of course, they're slightly different because now T1 is at the bottom and T2 is on top, which means the angles are of course a little bit different. So if T1 was here, this means this would be 25 degrees. So the angle here is 65 degrees. T2 would be 50 degrees from the horizontal. That makes this 40 degrees. That means here would be 50 degrees. So the angles are slightly different, but they're correct for T1 and T2. So whether you're calculating or using the scale diagram method, you can use either triangle because both triangles are correct for this situation. So let's start with the calculation method first. If we take a look at this diagram, you can see in this situation, we have an object that's 10 Newton weight suspended by two strings which are tied at angles that are not equal to each other. I've also added a blue line here to indicate the direction of the weight. And as you can see, the weight is acting from the center of mass of this object. So in this question, we need to calculate T1 and T2. Starting off with the calculation method first, just like for forces that are equal to each other, you can either solve this using the triangle of forces or you can resolve the forces. I will show you both. Let's start with the triangle of forces first. So if you don't know how to draw the triangle of forces, like I said, please watch the other video first because in that video, I talk about what this triangle of forces are and how to obtain the triangle of forces. Let's get right to it in this video. So starting with the weight line, because the weight line is vertical, so that's the easiest for us to start drawing. This is the weight line. So I'm just going to label that so that it's a lot clearer. The weight line has a value of 10 Newton in this case. Remember that for the triangle of forces, you can either go this way or you can go that way. It doesn't matter. But in my case, I can't do T1 because there's no space. So let's do T2. So same angle, same direction. And we'll finish up with T1. So this is T2 and this is T1. In addition to drawing the triangle of forces, you also need to label where the angles are. So as you can see on this section, T1 is acting 25 degrees from the horizontal. So I'm going to draw a dotted line here. This would be 25 degrees, which means the internal angle here is 65 degrees. For T2, it's acting at 50 degrees from the horizontal. So over here, T2 is a horizontal line. This would be where 50 degrees is acting. To get this angle here, you can use the Z rule, and this would be 50, which means if this is a right angle, this obviously has to be 40 degrees. And just like for this section, Z rule, this would be 25, which means the total angle on this side is 75 degrees. To solve this, we can use the sine rule. So remember, the sine rule is the length over the angle on the opposite side. The ratios for all three sides are the same. So if we take a look at this triangle, let's start with W first because it's a known value. So 10 Newton force, opposite side is 75 degrees. So sine 75. Let's take T1 next. So T1, opposite angle is 40 degrees. So sine 40. And T2, opposite side is 65. So T2 over sine 65. So to solve this, you just use the ratio. Let's solve for T1 first. So we have 10 over sine 75, and that's equal to T1, this is 7 by the way, over sine 40. So T1, using your calculator and punch it out, you would get a value of 6.655 Newton. Then do the same thing to calculate T2. So I'm going to take 10 over sine 75 degrees is equal to T2 over sine 65. Using the calculator, you would get 9.383 Newton. Now, if you have watched the other video, you would also have seen that I divided the triangle into two and I calculated T1 and T2 based on those right angle triangles. In this case though, we can't just divide this into two and say, okay, the top triangle is equal to the bottom triangle, and then when you divide into two, you take this as 5 and this as 5. It doesn't work in this case because the angles are not the same. So if I were to divide this triangle into two, you should be able to see that the triangles are not congruent because this triangle is 65, 25, 90, and this triangle is 50, 40, and 90. That means that the weight line is not divided into two equally. So you can't put 5 Newton and 5 Newton. So in this situation, you can't calculate it using the right angle triangle straight away like this. What you would need to do is you would need to resolve the forces of T1 in the x component and Ty y component, as well as T2 x component and Ty component. I'll show you how to do this. Alright, so in order to do this, what you need to do is you need to resolve T1 and T2 in the horizontal and vertical components respectively. So I'm just going to change a different color so that it shows up against the blue triangle. Let's start with T1. So T1 is going upwards diagonal to the left. So starting from this point, this would be where the component of T1x would be. So let's label it as T1x. That means the x component of T1. Do the same thing for the y, which is here. And this would be T1y. Now we're going to work on T2. So T2, let's keep the triangle on the inside here. So T2, this is the y component, and this would be the x component. So I'm going to label that here. So T2x and T2y. In addition to writing all the x and y labels, it would also be useful if you could write down the formula for the force resolution. That means if it's T1x, this would be T1 cos theta. Theta is 25, so I'm going to write here T1 cos 25. T1y would be T1 sine theta. Theta is 25, so let's write that here, T1 sine 25. And we're going to do the same thing for T2x and T2y. So this would be T2, this angle of 50, cos 50, and T2 would be T2y, T2 sine 50 degrees. So if you take a look, you can see that T1x is going to the left and T2x is going to the right, and the lengths are equal to each other. That means T1x is equal to T2x. That means T1 cos 25 is equal to T2 cos 50. So the problem here is that you have two unknowns, which means that in order to solve this, you need to do simultaneous equations. So this would be our first formula. Let's solve for cos 25 and cos 50 first to make it easier to solve it. So this would be 0.9063 T1. Let's write to 4 decimal places so that it's more accurate. And cos 50 would be 0.6428 T2. So this would be the first equation. For the second equation, let's look at the vertical. So you can see that W going down is equal to T2y plus T1y. Let's write it out. W equals to T2y plus T1y. We know that W is 10. T2y would be T2 sine 50, and T1y would be T1 sine 25. Let's solve for sine 50 and sine 25. Alright, a little bit lower here. So this would be 0.7660 T2 plus sine 25 is 0.4226. So this would be the second equation. So in order to solve it this way, what you need to do is you need to do simultaneous equation. That means from the first formula, you'd have T1 equals to 0.6428 over 0.9063 T2, which gives you 0.7093 T2. So substituting this into number 2, this would be 10 equals to 0.7660 T2 plus 0.4226, 0.7093 T2. You would get a total of 1.06575 T2. Solving this, you would get a value of T2 as 9.383 Newton. So then to solve T1, you take this and substitute into this equation, which would be 0.7093 times 9.383, which gives you 6.655 Newton. And that's how you solve it if you choose to use this method instead. So this is how you can use a triangle of forces. Now, if you plan to do resolution of forces, that means without drawing a triangle of forces, you would actually be doing the exact same thing. Let me show you. So if you want to solve this using the resolution of forces, you need to resolve T1x, T1y, T2x, and T2y. So let's say we don't have the triangle of forces, right? That means you can just use this diagram straight away. So what I'm going to do is I'm actually going to draw T1 and T2 horizontal and vertical components right in this diagram to save space. So using this line, let's use green. So if T1 is going that way, that means the horizontal component of T1 is going to the left, like this. I'm going to label this T1x. So this is the horizontal component of T1. And same thing for the vertical component, which is upwards here. So T1y is the vertical component for T1. And then we do the same thing for T2. So T2 is going upwards to the right, which means that T2x is going to the right and T2y is going up. Let me do a quick label over here. So you have T2x and T2y. Let's get the angles as well. So in the case of T1, if it's 25, Z rule, this would be 25 degrees as well. And then for the T2 triangle, this is 50. So that means inside here is also 50 degrees. So just like earlier, you actually need to write down the formula for the resolution of forces. So starting with the T1 triangle, because this is x, that means this is T1 cos 25, and T1y would be T1 sine 25. Just going to spill it over here because there's no space on that side. And same thing for T2. T2x would be T2 cos 50, and T2y would be T2 sine 50. So when the forces are in equilibrium, that means that the forces are balanced. So you'll find that the horizontal components have to be equal. That means T1x must be equal to T2x. That means T1 cos 25 must be equal to T2 cos 50. So just like earlier, you need to solve for the values that you know, which is cos 25, 0.9063 T1, as well as cos 50, which is 0.6428 T2. And then we also make the vertical values balance, which means that the weight going down is equal to T1y going up as well as T2y going up. We know that weight is 10, T1y is T1 sine 25, and T2y is T2 sine 50. Solve for sine 25 and sine 50 because these are known values. So you'd have 0.4226 T1 and 0.766 T2. So just like earlier, you need to do simultaneous equations. That means from formula 1, you would get T1 equals to 0.6428 over 9063 T2, which gives you 0.7093 T2. And we substitute this into number 2, which means that 0.4226 0.7093 T2 plus 0.766 T2. And this gives you the value of 9.383 Newton. And then to get a value of T1, you substitute your known value of T2 inside, which is 0.7093 times 9.383. And this would give you 6.656 Newton. So this is how you solve the question if you don't want to draw the triangle of forces. You need to resolve the forces first, and then you do simultaneous equations. So which one to use? You pick the method that you feel makes the most sense or is the easiest for you to solve. So for the scale diagram method, just like the solution for the forces where the angles are equal to each other, you do need to get a sketch of the triangle of forces first. Get the sketch done first before you start drawing, because it will make it so much easier for you to obtain the answer. Now, to show you the scale diagram method. So just like for the forces in equilibrium where the forces are acting at an equal angle, you also need to get a long ruler with length markings, a protractor, and of course, a pencil. Now, to maximize the space on this blank A4 paper, I'm going to use a scale of 2 centimeters to 1 Newton. We're going to draw the triangle of forces based on the sketch we saw earlier. The value of weight is 10 Newton, which means that based on the scale, the length of the weight line should be 20 cm. So using the long ruler, I'm going to draw out a 20 centimeter length. So from here to here. Now when you label, remember you only need to label the force value, you do not need to label the length. We know that T2 is acting 40 degrees from the vertical. So using the protractor, we measure out 40 degrees here. I'm just going to make a horizontal marking as well so that the label would be more complete. Now, to draw the tension line, we don't know how long the line should be. Never mind, just draw for as long as you can, and we will figure out the length later. Just for completion, I'm going to draw the horizontal line, but because this is not an actual force line, we draw this as a dotted line. This angle is 40 degrees and this angle is 50 degrees. Don't label T2 yet because we don't know where it ends. So if you don't know where it ends, how do we solve this question? What you do is you draw T1 because you know T1 ends at this point and it's acting at an angle of 65 degrees from the vertical. So using a protractor, we measure out 65 degrees, and I'm going to make the horizontal marking here just for a more complete diagram. So again, the horizontal line is drawn as a dotted line because it's not an actual force line. And now for T1, connect this point to the marking we've made. And can you see, even though we don't know the length of T1, but it forms an intersection point with the other line that you have drawn? So this is how we get the values of T1 and T2 using the scale diagram method. So this is T2, I'm going to label this as T2, and this is T1, I'm going to label this as T1, and complete the diagram with the angle markings. So in order to obtain the values of T1 and T2, because it's a scale diagram method, what you need to do is you need to measure out the lengths. So let's measure T1 first. So T1 has a length of 13.3 centimeters. In order to obtain the magnitude of the force, what we need to do is we need to use the scale and convert it back to Newton, which means the magnitude of T1. So take the length and divide it by 2. So this will give us 6.65 Newton. Do the same thing for T2. So I'm going to measure out the length of T2, which is about 19 centimeters. So the length of T2 is 19 centimeters, which means that the magnitude of T2 is 19 divided by 2, which gives us 9.5 Newton. So you may find the numbers slightly different from the values you've calculated, but that's only to be expected because calculation gives you a far more accurate number. The drawing, it depends on the scale that you have used. Of course, the larger the drawing you have made, the more accurate your numbers would be. So this is how you use the scale diagram method to solve questions for forces in equilibrium where the angles are not equal. So I hope you have found this video helpful in helping you find out how to solve problems of forces in equilibrium for forces where the angles are not equal, whether through calculation or scale diagram method. Thank you for watching. Don't forget to click like and hit subscribe. Happy studying!